Hello dear students, welcome to the class of high voltage engineering. Today I am going to discuss about the various techniques used to generate the high voltages and the currents in high voltage laboratories. So as the name suggests, generation, okay, it means that the term is related to the production of the voltage, or the, in other words, the induction of the voltage. So now why we need the various methodologies or the various equipments to generate the higher voltages from the low voltage, available low voltage in high voltage laboratories. So you can see in the photographs the various equipments are there which produces the different form of the higher voltages. So as we are considering the high voltage laboratory, the requirement of this laboratory is to assess or to test the quality of the insulation as well as the quality of the high voltage equipments. So based on the assessment, uh, one can get to know about its remaining life. Okay, so if we are considering the power plants, we are using normally the generators which induces the voltage. So in power plant, the generators used to generate the voltages produces or induces the voltage up to 13.2 kilovolt. But in case of the high voltage laboratories, where we are assessing the quality of the insulation or the quality of the equipment, the voltage they need to assess this quality, assess the properties, assess the performance characteristic is very high. Let me give you one example. Suppose I want to test the line insulator which is connected in 220 kilovolt overhead transmission line. Now I suppose to determine its performance characteristic. So the voltage that I need to evaluate its performance characteristic is 220 kV. That is the nominal voltage. Suppose I want to check its quality under the impact of this 220 kV AC power frequency voltage. Now if we are taking the case of our electricity board, they will give us maximum of 11 kV supply, which is 3-phase supply. Okay, and the generator produces how much? 13.2 kilovolt. So if to test the insulator, available insulator at 220 kV, okay, the generator becomes too much costlier. Actually it is practically impossible to design the generator to produce or to induce the voltage level of 220 kV, because if you have visited the power plant, you have observed the size of the generator which only give us 13.2 kV or roughly 11.2 kV. Okay, so you just think of the size of the generator which is required to generate or to induce the voltage level of 220 kV. Okay, so it is practically impossible to create a design of the generators which can give you the 220 kV of supply, which is actually your need to test the available insulators at 220 kV. So what could be the feasible solution? To connect the step up transformers so that you can produce 220 kV, and by using that 220 kV you can test your insulation. So in high voltage laboratory, the maximum input voltage which is supplied by the electricity board is 11 kV, Okay, and afterwards the transformers are connected, which are known as a step up kind of step up transformers. Okay, so these transformers are the high voltage transformer which produces the small input voltage, which produces the or which give us the higher voltage from the lower input supply. Okay, so there are so many techniques available to produce the different forms of the higher voltage, because to evaluate the quality of the insulation, to evaluate the quality of the high voltage equipment, it needs to be passed through the application of different voltages. Okay, different types of voltages. It may be the it is like the high voltage DC. Okay, then the higher AC voltages at power frequency, higher AC voltages at high frequency, the impulse voltages of long duration, impulse voltages of short duration likewise. Okay, so to produce this higher voltages, to produce this high voltage DC, high voltage AC, and the high impulse voltages, the various types of equipments you can observe when you are visiting the high voltage laboratories, or even when you are working in any manufacturing industries. So this is the flow that how we are going and attending the uh, all the techniques which are used to generate the high voltages and the high currents. So as I said, the different forms of voltages are there, which are intensively required for different applications. So high voltage DC, you may found its application in the particle accelerators in the nuclear physics. You can find its application in electrostatic precipitators, where the high voltage DC is used to remove the ionic impurities from the flue gases. You can also find its application in the impulse generators as a as a uh, as a charging source for the capacitors. Okay, so here you can see that high voltage DC is not only for the purpose of the transmission, but when it comes to the high voltage laboratories, they are utilized for the purpose of charging the capacitor banks of the impulse generators, as well as if suppose you want to study about the particle accelerations in nuclear physics, then again it needs the high voltage DC. If suppose you want to study the corona discharges under the polarity influence, then the high voltage DC is the best option. The high voltage AC of 1 million volts or even more are required for testing the power apparatus rated for the extra high transmission voltages, where the voltage level is more than 400 kV is to be assumed to consider EHV. High impulse voltages are required for testing purposes to simulate the overvoltage that could occur in power system, either due to lightning or even due to the uh, system faults. Okay, so these are the some sort of the applications that you may found its existence in the high voltage laboratories. So let us see the different forms of the high voltages which are likely to be generated in the high voltage laboratories. So one is high DC voltage, second is high AC voltage at power frequency, third is high AC voltage at high frequency, fourth is high transient or impulse voltage of very short duration, which ideally simulates a lightning over voltage, and transient over voltage of a longer duration, which simulates actually the switching surges of a longer duration. So let us quickly move on the generation of high voltage DC. So let us see the applications first. So as I said, it is used to charge the capacitor banks in impulse voltage generators or in impulse current generators. used in electrostatic precipitator, which you can see in the power plants. For testing the insulation of cables and capacitor, it needs high voltage DC. To investigate the behavior of insulation under the DC stresses, again it needs high voltage DC. So how it can be generated? So it can be generated either by using the half wave rectifier circuit or the full wave rectifier circuit, voltage doubler circuits, voltage multiplier circuits, electrostatic generators, Van de Graaff generators. So these are the methods through which the high voltage DC is generated in high voltage laboratories to fulfill the requirement of the testing. High voltage AC at power frequency can be generated by using testing transformer, which is usually a single phase step up transformer. The design of this testing transformer is completely different compared with the design of the power transformers and distribution transformers used for the transmission and distribution of the power. So now as the name is given as testing transformer, it means that the transformers are specifically designed to provide the test voltage only. Okay, the kVA rating of this transformer is obviously low as compared to the kVA rating or MVA rating of the power transformers and distribution transformers. So testing transformers are normally available in single phase. So high voltage AC generation at power frequency can be done by using single unit of testing transformer, or you can connect two or three transformers in series to produce the higher voltage at power frequency. The another approach that you may take is to use the resonant transformer, which is the transformer operates under the resonance principle. So these are the three methods or three equipments through which you can generate high voltage AC at power frequency to get the required test voltage at reduced cost. The high voltage AC generation at high frequency is produced by the Tesla coil. So Tesla coil is nothing but it represents the mutually coupled resonant parallel resonant circuitry. So the application of the Tesla coil is to study the sparks in the high voltage laboratories. The impulse voltages of longer duration and the shorter duration wave is generated by the impulse voltage generator. So these are the techniques used to generate high voltage DC, high voltage AC and the impulse voltages in high voltage laboratories. So let me show you some photographs so that you can have a better idea that how these equipments looks like when you are visiting in the high voltage laboratories. So here you can see this will represents the high voltage DC test setup. Okay, this is the voltage multiplier circuit which produced 2000 kilowatt, and to measure the voltage generated by this voltage multiplier circuit, the resistance potential divider is used. At its base you can see one grounding structure which is automatically operated, because once the testing has been completed you need to discharge the equipments. So discharging of the equipment is provided by this automatic grounding system. So when you energize this grounding switch, it will discharge all these high voltage terminals and the associated components. This is the resonant transformer, the cascade connection of resonant transformer. So you can see this is the first stage, this is second stage and this is third stage. So your three transformers are connected in series to produce the high voltage AC at power frequency using resonant principle. This is AC voltage divider for the measurement of the high voltage produced by this resonant transformer. You can consider the size of the equipment with respect to the height of this person. This is the another arrangement of connecting the transformers in cascade. So previous one was actually representing indoor facility. This one represents the outdoor facility. So here you can see that the first stage of transformer is put up onto the ground, then the second stage is placed above the ground level, and third stage is also placed above the ground level, equal to the height of the total height of the second stage unit. So here now again you can see that maximum 3 number of transformers are connected in cascade. Okay, so this is the one another connection of the cascading transformer. This is the photograph which is of the two stage cascade transformer available at CPRI Hyderabad. Okay, so this is the potential divider to measure the high voltage generated by this cascaded transformer. So you can compare the size of this circuitry compared with this building structure. This is the spark gap of impulse voltage generator. The upper photograph at left side, okay, this is the triggering circuit of the impulse generator. This is the multi-stage impulse voltage generator, Marx impulse voltage generator the to produce the over voltages or the impulse voltages of either short duration or the longer duration. To measure these voltages, the sphere gap assembly is used. So this upper photograph, which is indoor facility, the setup representing the test on the transformer. So you can look at to the size of the transformer compared with the person. The lower photograph represents the outdoor application, where this one indicates the impulse voltage generator, this is the potential divider circuit, and this is the circuit breaker which is under the test condition. So this is outdoor facility. This is ultra high impulse voltage generator, 1200 kV by 120 kilojoule to 7200 kilovolt to 720 kilojoule. So this is triggering gap, this is impulse voltage generator, and this is potential divider for the measurement of the generated impulse. This is impulse current generator, okay, which produce 8 by 20 microsecond of shock wave current to a peak value of 200 kiloampere and also 100 kiloampere of a longer duration. So same circuitry can be utilized by modifying some compartments or the components to achieve the or to simulate the lightning impulse currents and the switching impulse currents. So let us start with the high voltage DC generation. So half wave and full wave rectifiers. So rectifier may be the electron tube or solid state device. So nowadays single electron tubes are available for PIV, peak inverse voltage up to 250 kV, and semiconductor or solid state diodes up to 20 kV. So you can see that if suppose I am using this solid state devices, okay, to convert AC into DC, it has a voltage level up to 20 kV only. So to increase or to achieve the higher voltage, several units needs to be considered connected in series to obtain the higher voltage levels. So when the number of units are connected in series, there might be some problem, like the transient voltage distribution along each unit becomes non-uniform. Okay, so it may cause a damage to the element of the diode. So in this case, to prevent the damages against the non-uniform distribution of the transient voltage, the special care needs to be taken to make the distribution uniform. So we will see in the upcoming slides that how the protection can be given to the diodes which are connected in series to form the high voltage diode or solid state diode. So for application up to 50 kV and above, the rectifier valves are used, which consumes a special kind of construction. You cannot compare the construction of the diode that you are using in your electronic circuitry with the construction of the diodes which are connected, or diode elements which are connected in series to make it applicable for the high voltage applications. So what sort of the difference that you can found in the construction of this high voltage diode? So apart from the filament, usually you see the cathode and anode. So they contain a protective shielding or sometimes grid around the filament and the cathode. Now why this shielding is provided? Okay, why this shielding or grid is generally provided? So see, the anode is usually a circular plate. Now when now when the voltage is applied, there will always be the electrostatic field gradients. Okay, there will always be the electrostatic field gradient. So as a result, the cathode will experiences the large electrostatic forces during its non-conduction period. Non-conduction, it means that when the diode comes in a reverse bias condition. Okay, so under the reverse bias condition, the material is acting as an insulation. So now as it behaves as an insulation, it will always experiences, or it will always create the electrostatic forces. So these electrostatic forces are too much large and seen by the cathode. So to protect the elements which are connected in series against these electrostatic forces, the anode is kept to be fixed to a valve which is covered on the one side, and the on other side the cathode and filament are located, which has a steel mesh kind of structure. It means that the cathodes and filaments both are housed by steel mesh structure. Okay, so it generally produce a one protective grid. Okay, so this protective grid will cause the distribution of these electrostatic forces uniformly across the structure. Okay, so as a result, because of this uniform distribution of these mechanical forces, the cathode and anode both will gets protected, otherwise it will damage the structure. So in modern high voltage laboratories and testing installations, the semiconductor rectifier stacks are commonly used to produce the DC voltage. Okay, so semiconductor diodes are not a true valve since they have the finite but very small conduction in reverse direction. So it will give you the PIV value. So more commonly preferred diodes for high voltage application are the silicon diode with peak inverse voltage of 1 kilovolt to 2 kilovolt. So for laboratory applications, the current is very small. So selenium element stacked with peak inverse voltage up to 500 kV may be employed without the use of any voltage grading capacitor, but the cost of this stack is obviously higher than the cost of the silicon diodes. So you know the circuit arrangement of the half wave and full wave rectifiers. So how they look like in the industry. So here I am simply representing the arrangement for the half wave rectifier. So single phase AC input is there. Okay, so single phase variac is used to give the, or to vary the input voltage to the high voltage transformer. Okay, so this is your testing transformer, which is type of transformers. So at primary side you can see the three terminals. So one terminal is phase terminal, second is neutral terminal, and third is for the earthing purpose. Okay, the grounding, for the grounding purpose. So the single phase variac, which has two terminal, phase and neutral. So phase is connected to phase of the high voltage transformer at primary side, and neutral with the neutral of HV transformer. This big one is your secondary terminal. So this secondary terminal is connected with this high voltage diode. Okay, so from the diode at the output side you found that the load is connected. So load resistor represents generally the insulation that you are being to connect for your investigation. And capacitor filter, the requirement of this capacitor filter, which is also a high voltage capacitor, to remove out the ripples which are produced when there is a conversion of AC into DC. Okay, because if you are not eliminating the harmonic components from the generated DC voltage, then it may causes the damaging effect to the insulators, or sometimes you may not get the actual investigation. Okay, so in short, with the presence of this harmonics, we cannot judge the quality. So to judge the quality of the insulation under the DC stress, first we need to remove the ripples or the harmonics associated with generated DC. Okay, so let us quickly understand about how it generates the higher voltage. So let us consider the half wave rectifier. So input is AC. So here I have represented its waveform. So AC has a positive and the negative cycles. So from 0 to pi, you will have the positive half cycle. From pi to 2 pi, you will have the negative half cycle. So during positive half cycle, you have the plus Vmax value, and during negative half cycle, you have the minus Vmax value. So let us assume that this is point A and this is point B. Now we have two options. One, that I am going to discuss when the capacitor is not present and when the capacitor is present. So we have two cases to discuss. So let us take first case without capacitor. So you can see in this circuitry that capacitor is disconnected. So how this circuit behaves, and what could be the impact that you can observe across these load side. So let us consider this point A and point B. So during the positive half cycle, during the first positive half cycle from 0 to pi, point A becomes positive with respect to point B. So in this condition, the current is flowing in this direction. So as this is the direction of the current, you can see that this diode comes in a forward bias condition. So you know that when the diode comes in a forward bias condition, it acting as a closed switch. Okay, so now it will get short circuited. So the now maximum potential, the positive maximum potential, is now available to this RL side. Okay, so here I am drawing the waveform of the output voltage with respect to theta or time axis for the circuitry when it do not contain capacitor filter. So during positive half cycle, I am getting the voltage. So when point A becomes positive with respect to point B. Now as you can see that from pi to 2 pi, the input voltage wave attains negative polarity. So suppose A is now becomes negative with respect to the point B. So in these circumstances, the direction of the current will now get changed. Okay, so during this reverse bias condition, during this reversal, this will be the direction of the current. So you see that during this condition, during the negative half cycle from pi to 2 pi, the diode comes under reverse bias condition. So now as the diode is in reverse bias condition, it will acting as an open switch. Okay, so current in the circuit is 0. So voltage VL, that is the load voltage, which is given by or calculated by I into RL, is also 0 because current in the circuit is 0 as the diode acting as an open switch. So during reverse bias condition, I am not getting any output voltage. Further, from 2 pi onwards, you can see the wave attains positive value, so I am getting the Vmax. Okay, so this will be the waveforms that you are achieving. So here now I have the two limits. One is Vmax limit, okay, and second is Vmin. That Vmin is 0 value. This is my Vmin value. This is Vmin value. So you can see over here delta V. This delta V represents the oscillations that is being present into generated output. Okay, the output of this diode, output of the rectifier is always oscillating in nature. So here you can see that my output voltage when capacitor filter is not connected is oscillating between Vmax and Vmin value, where Vmax, that is the maximum voltage supplied by the transformer during the positive half cycle, and Vmin, that represents the voltage available at the load side during the negative cycle of the input voltage. So Vmin is in this case is 0. Okay, Vmin is 0. So this delta V, the delta V which represents ripple voltage magnitude, which is given by the equation of Vmax minus Vmin divided by 2. Delta V is the half of the difference between the maximum voltage and the minimum voltage. So this delta V, the ripple voltage magnitude in case when capacitor is not connected, is Vmax minus 0 upon 2 is equal to Vmax by 2. Okay, it is Vmax upon 2. So you can see the tremendous value of the ripple voltage is now present. Okay, which may create the error during the investigation or during the study of the insulation performance or insulation behavior under the application of high voltage DC. So if I am considering the ripple factor, then ripple factor is very high in this case when the capacitor is not connected. Okay, so what I need to do, I need to remove this harmonic. Okay, so to remove this harmonic, I need to connect the capacitor. So let me first wipe out this. So now the second case is the behavior of the circuit when the capacitor is connected. So here you can see that now I have connected the capacitor, okay, at the output of this diode. So now let us see what exactly happens when the capacitor is connected. So again, during the positive cycles you will get the voltage. Okay, let us consider the positive half cycle where point A becomes positive with respect to the point B. Okay, so this will be the direction of the current. So during the positive half cycle, this diode comes in a forward bias condition. So as a result, it will acting as a closed switch. So under this situation, this transformer secondary performs two duties. One, that it will charge the capacitor to the Vmax value, and second it will also supply load current to the load side. Okay, so if we are considering the time taken by this input voltage to supply the load current is very small. Okay, then whatever the energy has been supplied by this transformer is available to charge the capacitor only. So during your positive half cycle, the capacitor will charge to maximum value. Okay, the capacitor will now charge to a maximum value. So point E represents that the voltage across the capacitor is now becomes equals to Vmax. Okay, becomes equals to Vmax. So when your input voltage achieves Vmax value, the capacitor voltage also achieves Vmax value. Now as you can see that in the first waveform, the input voltage waveform, the voltage of input is now reduced to zero side. Okay, so now as it reduced to zero, it means that the voltage of this capacitor, suppose I am representing it as Vc. Okay, so when the input voltage achieves maximum voltage, the voltage across capacitor also becomes maximum. Okay, so from 0 to pi by 2, from 0 to pi by 2, there is a increase in the potential to this input voltage. As a result, it will charge the capacitor to a Vmax value. Now from pi by 2 to pi by 2 to pi, the input voltage will reduce to 0. Okay, so this will represents that the voltage across capacitor becomes greater than the input voltage Vs. So under this situation, as the voltage across capacitor now becomes more than the supply voltage, the direction of the current will now gets reversed. Okay, so this will be the direction of the current. So now the capacitor will now supply the current. Why? Because as capacitor voltage is more than the supply voltage, this diode comes in a reverse bias condition and acting as an open switch. Okay, so the current into this circuitry is 0, whereas the current in this load circuit is maximum. So now the capacitor is delivering its current to the load side. So now as the capacitor will deliver the current, okay, pushing the electrons, the capacitor will discharge. So here you can see that from E to point F, there is a discharging phenomena of the capacitor. So this will represent that the capacitor is now driving the load circuit. Okay, so as a result, whatever the energy has been stored by the capacitor is now gets released, and that phenomena is known as a discharging of the capacitor. So at the point F, the voltage across capacitor at point F, voltage across capacitor becomes lower than the voltage of supply. Okay, at point F, the voltage across capacitor becomes lower than the supply voltage. So now what is the process? Now again the capacitor will start to charge to a maximum value. Okay, and then once the voltage across capacitor becomes higher than the voltage of supply, the diode comes in a reverse bias condition, and the now capacitor is now driving the load circuit. So in this case, now you can see that point E represents the maximum voltage and point F represents a minimum voltage. So when I am comparing delta V value that I am getting when capacitor is not connected and when the capacitor is connected, it is quite less. Okay, so it means that when we are using this filter or the capacitor at output terminals of this rectifier circuit, then we can achieve a closer value as of our requirement. Okay, so elimination of the harmonic will now provide us a very good result during the investigation. So one point which we need to understand in this case is alpha t term. This alpha t. Okay, here you can see the two things are there. So this is normally known as conduction time. Conduction, it means the time from which the diode gets conducted, because it needs a minimum potential to conduct it. Okay, so at initial conditions there is no conduction, but as the voltage across this diode is sufficient, then it will starts conducting, and as it starts conducting, it will acting as a closed switch and and filling up the charges to this capacitor. So as a result, the capacitor will charge to a maximum value. Okay, so alpha t that represents the conduction time of the diode to allow the charging of capacitor to a maximum value, where this alpha is very less than the 1. So once we are considering this alpha very much less than the 1, then we can emit the component of the current supplied by this transformer to the load circuit. So as a result, the total energy supplied by the transformer is utilized to charge the capacitor. Okay, so this will be the case that we can observe during this operation of the half wave rectifier with the capacitor. The another point which we need to consider is during the negative half cycle. So when point A becomes negative with respect to point B, the direction of the current gets reversed. Okay, so now as the direction of the current gets reversed, the maximum voltage which is available at the diode side. Let me first wipe out the thing so that you can easily understand what exactly the meaning that I am going to discuss. Okay, so point A is now negative with respect to point B. So as a result, now the direction of current is reversed. So initially during positive half cycle, the capacitor is charged to Vmax value. Okay, so now as the direction of the current is changed, okay, from positive to negative, the net voltage available at this diode side is now becomes Vmax plus Vmax. So 2 Vmax of voltage is now available at the diode side. So Vmax that is supplied by this point A, which is negative in polarity, and second the voltage of this capacitor at this point. So potential difference between point A and point C will be 2 Vmax. So Vmax minus of minus Vmax at A will give you 2 Vmax value. So diode which you are selecting for the purpose of this high voltage DC generation must have capacity enough to withstand the double voltage during the reverse bias condition. Okay, the third point is, you can see that this alpha t value is very less than the half of the cycle. Okay, it means that the capacitor is instantly charged. So charging and discharging phenomena depends upon the RC time constant. So we are very much interested to get this discharging phenomena. So discharging time depends upon RLC time constant. Okay, the another point is from point F to point E. Okay, from point F to point E, it means alpha t duration. So alpha t duration represents that the transformer, secondary of the transformer, will serve two duties. One duty is it refills the charge which are lost by this capacitor to drive the external load circuit, and second, the current supplied by this transformer secondary to the load side. But generally we are eliminating the component of the current which is driven to the load circuit because of this lesser value of alpha. So whatever the energy has been supplied by this transformer is entirely available for charging of the capacitors only. So this is how these rectifiers are working. So this is what I have discussed with you. So here the representation is done on the basis of the loading condition. So when the rectifier is under the no load condition, and what will be the waveform when the rectifier is under the loading condition. So according to the IEEE standard, the value of DC voltage is actually defined by its arithmetic mean value. So it is expressed as Vd is equal to 1 upon T, 1 upon T integral 0 to T V of T dt, where T represents the time period, okay, time period for completing the one cycle. So if I am considering the complete cycle, so the T is the base, so it is 1 upon 2 pi integral 0 to 2 pi Vm sin theta d theta. So V of T is your sinusoidal voltage. So when I am taking the integration, okay, if I am taking the integration, at the end I am getting the mean voltage value for this half wave rectifier is Vm upon pi. Okay, so this will be the mean value of the voltage. The magnitude of the ripple voltage denoted by delta V, which is defined as half the difference between maximum and minimum value. So it is given by delta V is equal to V max minus V min upon 2. So if we are not connecting the capacitor, then delta V is V max upon 2. So only half of the value we are getting, okay, which is our expected, which is not our expected one. So to remove this ripples, we need to connect the capacitor at the output terminals of the rectifier circuit. The ripple factor is defined as a ratio of ripple magnitude to the mean value. So when I am taking the ratio of delta V to the mean voltage, I am getting ripple factor. So this ripple factor should not be more than 5%. So if you are not taking the case of the capacitor, then the ripple factor will be pi by 2. So how? So as you can see in the previous equation, that the, Vd is mean value is Vm upon pi, okay, and delta V if capacitor is not there, then delta V is Vm by 2. Okay, so when I am taking the ratio of this delta V and Vd, I am getting ripple factor of pi by 2 value, which is comparatively large. Okay, so we need to reduce this amount of ripple to get the expected value of the output voltage for our insulation study under the DC stresses. Okay, so to achieve this limit, we are generally connecting the capacitors, so it will be further reduced. So both full wave and half wave rectifiers produces a DC voltages actually less than AC maximum voltage. That is because of the voltage drop seen at the diode side, and second due to the loss of energy observed when there is a transformation of charge from capacitor to the load side. Okay, the third is also when the ripple gets removed by the capacitor. Also the ripple or the voltage fluctuation will be present, and this needs to be kept within a reasonable limit, so that we are using the filters. The magnitude of the ripple voltage, as you have seen for the half wave rectifier, is delta V, which is equals to V max minus V min by 2. So it could be further simplified to the delta V is equal to I by 2 Fc. So this equation will actually help us to get the value of the capacitance of capacitor to obtain the specific range of the ripple factor. So let us derive this equation. So let us assume that at any time the voltage of the capacitor is V. Okay, let us assume that the capacitor is charged to a Vmax value. Now when the voltage across capacitor becomes more than the supply voltage, you have seen that the diode comes in a reverse bias condition. So now it is a duty of capacitor to supply the load. Okay, so now as the capacitor supplies the load, it will discharge, and once the discharging of the capacitor has been observed, the voltage is reduced. So suppose the decrease or decrement or reduction observed in the capacitor voltage at any time is supposed to dV at time of dt. Okay, so the charge delivered by the capacitor during this time is dq is equal to cdv, because q is equal to cv. Okay, so when there is a change in the voltage, there will always be the change in the charge, so dq is equal to cdv. So if the voltage, as you have seen that the voltage changes from Vmax to Vmin when it supplies the load. Okay, so charge which is delivered by this capacitor by considering this limit is represented by the integral form. So integrating dq from this limit Vmax to Vmin, because it supplies the energy to the load from Vmax to Vmin. So integrating Vmax to Vmin CdV, it will bring this equation minus C Vmax minus Vmin. Okay, so in other words, the charge Q is equal to C into Vmax minus Vmin. So Q is equal to 2 delta CV. Okay, delta V, that is ripple voltage magnitude, which is difference, half of the difference between Vmax and Vmin. So Vmax minus Vmin divided by 2. So from this equation, the difference is 2 into delta V. So 2 into delta V into C. Now Q is equal to IT, as you can know it. Okay, it is a product of current and time. So from this formula we can obtain delta V is equal to I upon 2 FC. Okay, so now from this equation one can get to know that how we can control this ripple voltage magnitude. So either you can change the value of load current, or you can change the value of frequency, or you can change the capacitance value. So this load current value depends upon the load. So we are actually connecting fixed load. So it is impossible to, or it is not a feasible solution to control this delta V by controlling this load current value. Okay, because if you are changing the load current value, ultimately you are changing the input voltage, but we need to test our insulation at a fixed voltage value. Okay, so the control of the delta V by controlling the load current is not a feasible solution. So now we need to think of the two parameters. One is the frequency and second is the capacitance of the capacitor. So this frequency is the frequency of the supply. So if I am changing the frequency, to control this delta V value, it may affect the performance of the high voltage transformer. Okay, here you can see that delta V is inversely proportional to the frequency of supply. So if suppose I am increasing the frequency, obviously from this relation delta V can be reduced, but if I am increasing the supply frequency, then it may causes the unnecessarily overheating problems with the transformer. Okay, so the insulation of the transformer may get damaged due to the overheating when we are increasing the frequency. So again I cannot see it as a feasible solution. So we have only the one parameter through which we can easily control delta V value. So the selection of this capacitance to a higher value can brings the delta V to a very low value. Okay, so this will be the feasible solution to obtain the very low value of ripple voltage magnitude, and as the delta V goes down, the ripple factor also goes down. So at the end we will get the required value of the high voltage DC to test our insulation satisfactorily. Okay, so this is about the half wave rectifier circuit, which you can also simulate in the MATLAB platform to study the operation of this half wave and full wave rectifier circuits. So in the next lecture we will see the voltage doubler circuit, because half wave rectifier circuit and the full wave rectifier circuit normally give us the Vmax value. Okay, so if suppose I am giving 30 kV AC as input to the diode, it will give me roughly around 25 kV AC, or something 26 or 29 kV AC. Okay, so if suppose I want to test the insulation at 60 kV when the available source voltage is of let us say 30 kV only, so in that cases I need to go with the voltage doubler circuits to produce the double voltage. Okay, so in the next lecture we will see the voltage doubler circuit and the voltage multiplier circuits. Thank you.